Okay, hello. Happy Monday. We made it to week 5. I shouldn't tell you this, but the physics professors made a poll at the beginning of the semester on which week in the semester we thought we would get shut down for good. And I had week 5, so I hope I'm wrong. But this is the week. So far, so good, though. Everybody's doing a great job. I've been actually amazed at how well we've done as a college, keeping the numbers down. So hopefully, it will be Thanksgiving week and not any sooner than that. Okay, weird week this week. As you know, there's a half a Kappa set up that's due Thursday at the usual time. We do not have class on Wednesday because it's Rejuvenation Day. So rejuvenate yourselves. We will certainly be through. I sort of have a half a class of stuff today to present. We're not going to go on to the next section. I'll open it up to questions maybe. We'll see when we end. So the question was asked for office hours on Wednesday. I plan to be available for office hours on Wednesday, even though it's Rejuvenation Day. I'll probably be at home. So don't come to my office for office hours, but if you want to Zoom for office hours, I'll be available. The exam will be Friday in class. A few questions, some problem solving, some conceptual. We'll see how that goes. So far, only one person has indicated that they will not be taking the exam in class. So my plan is everybody else will be here, and the person who is not taking it in class will take it at the same time, and I will Zoom with them in the front and proctor that while I'm proctoring everybody else in the exam. Yes. It will be a paper exam. I will hand you a booklet. The online person, I will upload the thing that will be available starting at 1:30. You will work it out either on the packet. There'll be spaces to write in your work for each question. For my online person, I'll send that person an email when the time comes with all the details. But work on scrap paper and then take pictures of the scrap paper and upload it, basically. No, for people who are in class, you can have a couple of pieces of scrap paper if you want. That's not. I will, if you need some, I'll have some. There will be some extra room for doing scrap work on the exam if you need it. It will be self-contained though. All you need is a calculator. There won't be any numerical. I'm not going to be asking you to solve anything numerically. Everything you need should be able to be done on a calculator. Other questions? Yeah, are there going to be problems from Kappa 5 on the exam? Kappa 5, yes and no. Half of the Kappa 5 questions require some sort of numerically solved thing. So in that case, definitely not. However, the concepts that are in Kappa 5, namely the combined double and single slit, those kinds of things could show up. So that's a yes and no answer. I'm going to be going over Kappa 5 a little bit today at the end of class, or at the end of our material, which actually isn't all that much today. Other questions? Okay. We got this. By the way, just for future planning, I know that this week will consume us this week, but next week is coming. I will post a Kappa set on Friday for material that you've never seen before and we haven't talked about before. It will not be due the following Thursday. It will be due the Thursday after that. So next week will be a Kappa homework free week. And then we'll be a little bit ahead of the material. So I'll probably be done with covering the material for Kappa, the next Kappa, certainly by Friday of next week. But that's okay. You'll have, so we'll be a little bit ahead on the material compared to the Kappa, but that's fine, whatever. Okay, great. Then let us remember and remind ourselves where we were and what we were doing. We were numerically solving for where the maxima happen for the single slit diffraction pattern. And we, at the end of class, had gotten to, on Friday, the relationship, which is the maxima happen at a alpha where tan alpha equals alpha. All of the maxima, in fact, happen except for the central maxima. Well, even the central maxima, tan alpha is equal to alpha. Various regions where tan alpha equals alpha. That is the regions where the maximum is happening. Thank you. All I wrote was tan alpha equals alpha. Looks like I just got kicked off of sorry, Zoom people, looks like I just got kicked off, but I'm back on now. Let me share my screen again. Okay, now we should be back. You, I don't want you there. How do I move you? There we go. Or even down here. That would be fine. Okay, so as I was saying, tan alpha equals alpha. That is where all these things. And to remind you, alpha is defined to be alpha is defined to be, some days are technologically better than others. I don't really want you hanging out there. Oh, I haven't done, yikes. Oh, nope, that's not what I want to do. I want to pin my video. Okay, now that's good. Now I need to do top hat, sorry. Let's do some attendance. $14.27 for those who are here, thank you. Okay, and so you recall, alpha is defined to be pi over lambda times sine theta. So this is some, again, alpha is where we are in the diffraction pattern itself. Theta is where we are in physical space, but alpha, since it contains both information about L and X encoded in encoded in theta, and it contains information about the wavelength. I thought there was an A in here too. Am I missing an A? I am missing an A. It's A sine theta, yeah. Thank you. Pi over lambda A sine theta. A over lambda encodes how stretched out that thing is. And so alpha is a unique position of where you are in the diffraction pattern itself. So you may remember from last time, we solved this numerically using solver in Excel. Usually when I teach sophomore lab, which by the way, I have done every single semester I've been teaching in the fall, except for this one, we do solver like in week 2. So I'm a little surprised you haven't done it yet. But you're going to need it some sort of numerically solving technique for this week's lab, for this week's homework. So let me make this a little bit bigger and let me remind you what we did yesterday, because we're going to need to do it again, and you're going to need to do it for the homework in a slightly different way. So we made a cell for alpha, And we knew that it was going to be 4.5. How? Because when we plotted tan alpha versus alpha, we noticed that they equaled each other at about 4.5. So this is just a guess of where that first, there's one at 0, and then there's another one at about 4.5. And that's where we were at the end of class last time. And we had to figure out exactly where this was. So I made a guess of 4.5. Tan alpha, this is just tan alpha, is about 4.6. And that's a difference of 0.13. I know that if I make tan alpha bigger, tan alpha is also going to get bigger. So I am at 4.5, I'm too far in this direction. I need to come down a little bit, right? So I can say 4.9, and I've way overshot it. Oh, sorry, 4.49. I need to go down. I forgot the 0.49. So that is, I've gone too far, right? Now I'm on the other side. My alpha is bigger than my tan alpha. So I went from over here to over here. I am really close though. So again, you could just iterate here and get this number smaller and smaller until you get to the number that it should be. There is a solver thing that you can do though, and this is what solver does, is it iterates things until something becomes something else. And that's really what we want to do here. So if you need help getting solver loaded on your machine, you can send me an email. Maybe I'll post some instructions this week on Canvas. But it's not that hard. For Macs, it is literally as easy as going to Tools, Excel add-ins, and clicking the solver add-in button. That's really all you have to do. For Macs, I think you have to go to the File menu, open up Options, and then there's something in there called Excel add-ins. And then again, you're sort of getting to a menu that looks like this. You're checking the box that says Excel add-ins. And I'm sure you can Google it and find out how to do this also. Once you do that, the Data tab will have a okay, you can go away now. The Data tab will have something that says Solver on it all the way on the right-hand side. When you click the Solver button, this box will come up, and this is way too small for you to be able to see really what's going on, and I apologize for that. Let's see if I don't think I can make this any bigger, aside from totally messing up my display preferences. Let's see if we can do that. Why didn't my system preferences come up? Open display preferences. Yeah, okay, great. All right, where are they? Great. All right, sometimes things just don't work. That's fine. Anyway, so let me describe to you what this window looks like. In fact, maybe I'll draw what this window looks like here and point out what the different features are. Okay, you are now in the wrong spot. Okay, if I can get both of these on the same thing. Okay, here's what I'm gonna do. I'm gonna draw this. Okay, yep, great. So this is what this looks like. We've got a box that says set objectives. That is the box that you're going to be. So what is solver usually doing? I want to minimize this value. I want to maximize this value. I want to set this value equal to something. That's almost always what you're doing. The set objective box is the thing that you want to change, the thing that you want to be equal to something else, or minimize or maximize. So in this case, this is our diff. This is the diff cell. So since I started this with the diff cell highlighted, it's automatically put the diff cell in there for me. Since I hit the solver button with that cell already highlighted, it's already put that in there for me. I could certainly click a different cell and it would change it. I could certainly type anything I want in there. That's not an issue. The next thing it's asking me is, what do you want to do to that cell? And you have three choices. You can maximize that cell, you can minimize that cell, or you can set it equal to a value of something. For solver in lab, you're almost always going to want to be minimizing that thing, because you're going to be fitting some curve and you're going to be minimizing, doing a least squares fit. And it's the minimum of the sum of the squares of the best fit that's going to give you the best fit. Here, so min or max or set, what does it actually say? It says value of. Value of. And in this case, there's a little box here, and we want to set the diff to 0. So we're gonna put a 0 in that cell. I'm just gonna type 0 in that cell right now. Actually, I need to click the value of button, and 0 is the default. I don't have to put anything in at all. There's one other thing that you need to do. By changing changing variable cells. And there is another big box down here. This is where you put, so what is solver gonna do? It's gonna mess with this cell until this cell does the thing you want it to, minimize, maximize, or set to 0. So we need to change alpha, we need to set that to our alpha cell. It's gonna change alpha by small amounts until the diff cell goes to 0. That should be all you really need to know. There's another big box down here. There's one thing down here, which is make unconstrained variables non-negative. This is an important thing. It's not going to be important here. They're not going to affect us at all. What this prevents from happening is a certain value to go below 0. I'm shocked that this is checked by default, because almost always with what we do, we don't care if it goes negative. If we're fitting some x naught parameter, we're happy with that being positive or negative. And actually, it can mess you up to have this checked, and it's checked by default. It won't affect us now, but it might affect you later if you don't remember to do it. There's no reason to have that thing checked unless you really don't want that thing to go negative, meaning the alpha value as you go along. Okay. That's it. That's all you have to do. You click the solve button. Problem to solve, not specified. Oh, I forgot to put in the constrained variable. So I forgot to click on my alpha column cell, and now it says sheet 1, A2. And now if I click solve, it's going to think about it. It's going to think about it. And now it's going to give us, so it's going to show us the solution. And it's going to ask us if that's really what we wanted to do. It's possible that things have blown up and you can say, stop, take me back, I have to figure something else out. In this case, it has done exactly what we wanted to do. I'm going to keep the solver solution, click OK, and I've got it. Again, it's not perfect. It actually did better today than it did yesterday when we tried this, because we probably gave it a slightly closer value. And you can mess with the tolerances. You can make them bigger. You make them smaller. The smaller you make the tolerance, the more it will churn until it actually gets to the right number. But you can see we've got 1, 2, 3, 4, 5, 6, 7. They agree to 7 sig figs. That's pretty good. That's really all we need to know. It would have taken you an hour to get to this point, perhaps, fiddling it with it one at a time, iterating until you get to this point. Solver is a very useful tool for numerically doing these kinds of things. Great. So, what we're interested though, really, is what value of pi this is. So I really want to know what alpha over pi is. And that's going to be 1.43. Why is alpha over pi something that would be interesting to me? Let me ask you this. Where would we expect the maximum to be if this thing looked like the double slit pattern in the alpha space? Right. That's kind of, it's exactly right. That's kind of equivalent to M. That's right. So where would we, naively, if you were just looking at where the minima were for the diffraction patterns, right? Where do those happen? At 1 and 2 and 3 and 4. Those happen at integer values of M. Where do we expect the maxima to happen naively? 1.5. We would have expected this to happen at alpha equals 1.5 pi. Alpha over pi equals 1.5. And you can see that it does not quite do that. It's not far off, but everything gets shifted a little bit towards the center. It's a little bit less than 1.5. So this is 4.49. There's no intuition for what that looks like to me anyway, and what the alpha space looks like. But there is an intuition about alpha over pi. And that's your M value. And that will be integer values at the minima, but it's not quite half integer values at the maximum. Yeah. That's an excellent question. Where does the second maximum happen? The M equals 2 maximum. Let's find out. Is it regular? Great question. I'm so glad you asked it. Let's find out. We certainly are equipped to figure that out. So I'm going to use this plotting tool. You can use any plotting tool you want. You can use Excel for this. You just have to make some columns of alpha and tan alpha and plot them together and see where they go. Let's back up a little bit and go, let's say from 0 to, I don't know, 12. Aha! Now we've got more than one. We've actually got 3 of them. Okay, cool. So we know that this one is about at 4.5. It looks like this one is, well, it should be at 2.5 pi, right? That's a decent guess. What's 2.5 pi? I don't know, 7 point, there's 7, there's 7.5. I don't know, 7.7 maybe? Let's just drag all these down. 7.7 is a little bit less than 2.5 pi. But I'm not there. This isn't even all that close. So I need to run solver again to figure out what where the second maximum is. And let's see exactly where it goes. So let's run solver again. So I'm going to run this on C2 now. Nope, I'm running this on C3. And I'm changing cell A3. So to click on those two, click the solve button. It looks good. Click the OK button. Okay, so 2.459 pi. Does that look like a nice integer multiple of or something related to that first one? No, not really at all. In fact, these are all irrational numbers. And they're not really related to one another, aside from tan alpha equals alpha. They are the solutions to tan alpha equals alpha. And they are, but you notice this is a little bit closer to the center line where you would expect it to be than the first one was, which is interesting. Question? Good question. That's why we have to give it a guess that's pretty close. It starts off by varying it just a small amount. And so your initial guess is going to entirely determine which of these solutions it gets to. It will get to the closest one, basically, hopefully. You hope that it gets to the closest one. As long as you're fairly close to it, it shouldn't have too much of trouble doing that. But that's why you have to, I mean, if it runs off to infinity somewhere, that's where you can say, abort, send me back to my original and just try a different guess that's a little closer maybe. Yep. Yeah, let's see if we can answer that question graphically. The answer is yes. But let's see if we can see the answer to that question graphically. Let's go back to Mathematica. Okay, so this is the tangent function. Where does the tangent function go to infinity? The tan alpha goes to infinity and then back to negative infinity at those half pi points. That's exactly right. So what happens as alpha gets bigger and bigger and bigger? You're getting closer and closer and closer to, you'll never get to the half pi point. That's where tan alpha goes to infinity until alpha goes to infinity. But when alpha gets to infinity, you're high enough up on that ledge that you actually will get to the integer pi over the half integer value. Does that make sense? So you can kind of see graphically why it is that we get closer and closer to that actually being the halfway point between the two minima, because we get higher and higher and higher on that tan function, and that gets us closer and closer to the midpoint, which is that half integer value pi. Does that make sense? So I'll leave it as an exercise for you to do this yourself. I'm just going to write down the answers. So this is the single slit maxima locations. So first maxima, so first, zeroth is at the center. I'm not even gonna bother to write that one down. First maximum happens at, this is the alpha value, this is the alpha over pi value, and this is the maybe expected naively if they were all symmetric. So this happens at I'm gonna give you a lot of decimals here, 4.493409. This is alpha over pi of 1.430297. And you would expect this naively to happen at 1.5. Second maximum, 7.72525, 2.459024. You'd naively expect this to happen at 2.5. I'll do you one more. Third, at 10.90412. This is 3.47089 pi, which is pretty darn getting closer and closer to 3.5. You have everything you need to know now to solve problem 1 on the homework set. It tells you the different distance between the two first maxima on the diffraction pattern. Half of that value, of course, is the distance between the center point and that first maximum. You know what the alpha value of that first maximum is, so you can work backwards to figure out what the A value is, since you know what alpha is for that first maximum. It's 4. You don't have to solve that one again because I've already solved it for you. Just know that that first maximum happens at 4.493409. You can turn that alpha into a pi lambda A sine theta, and you'll know everything else in there. I think you can solve for A just knowing what the value of alpha is. Just plug in that value for alpha and solve for A. So you don't have to use numerical reasoning to do number 1. You will, although if you want to get that 4.49, you would have to. We'll talk more about the rest of it. I'm already 30 minutes into class. Look at that. We're making good time. Okay, so the last thing on this section is, of course, we've talked about double slit, we talked about single slit, but no double slit that you do ever has perfectly finite width slits. So really, anytime you do double slit experiment, you're really doing a combined double and single slit experiment because there's no way to get around it. You have to have finite width slits. So what does that look like? The combined single and double slit. Just put it all together. Remember, let's just write down what these things were. The double slit, the intensity pattern of the double slit we derived was I equals 4I naught times the cosine squared of delta phi over 2, where delta phi was defined to be 2 pi over lambda times d sine theta. On the single slit was defined very similarly. I equals I max times sine of phi over 2 over phi over 2 quantity squared, where phi is defined to be 2 pi over lambda times a sine theta. Whereas before, d is the distance between the slits, a is the width of an individual slit. Note that delta phi and phi are not exactly the same thing. Delta phi is the phase difference between the two slits. And phi is the phase difference across one slit. Okay, it's way easier to use alpha and beta as opposed to delta phi and phi. So let's just use our thing. We've already done this at some level. Let's use alpha equals phi over 2. And why not, since we're using Greek letters at the beginning of the alphabet, why not choose beta to be delta phi over 2? That's going to make this whole thing a lot easier. With those definitions in tow, all we have to do, and this is one of the cool things, to combine the double and the single slit together is just to multiply those two things together. And you get the combined double single slit pattern. So we can just combine the whole thing together by multiplying them together, and we get this. I equals I max times sine alpha over alpha squared times cosine squared beta. And that's it. It looks so simple. I just multiplied this by this, substituting in beta there and alpha there. And I combined all of these multiplicative terms on top, in front, to be a single I max. That was all I did. Reminder that, just so you have it in your notes here, alpha equals pi over lambda times a sine theta, and beta equals pi over lambda times d sine theta. A slit width, D slit separation. Also, I max, where this is a new I max, This is the, again, we're defining Imax here in the same way that we defined Imax for the single slit only, and that is the intensity that this pattern happens to have at the top of, at theta equals 0, at alpha equals 0. So really, then this new Imax is the old Imax times 4I naught. It's the combined amplitude of this thing at the very center. IM is the new max at theta equals 0. Okay, let's open up Mathematica again. Actually, let's go to here. Again, intuition is a good thing. Let's see if we can bring up this Mathematica sheet and make it bigger. Yep, enable dynamics, yum. Let's make this much bigger. Zoom. Nope, that's not what I wanted to do. Magnification, here we go, 200%. Oh, that's much better. There we go. So, oops, I've already given it away. What does this actually look like in space? So here is a single slit. This is our single slit diffraction pattern as we've seen before. What if we add a second, so it's a single slit. If we add another one over here, some ways away, then we get this looking pattern. It's just the combination of the two. You still have the single slit pattern, which you can see. And on top of that, you have the double slit pattern. Since D is much bigger than A, almost always these diffraction fringes, the interference fringes, which was what we call this flying up and down, happen much more frequently than the overall diffraction pattern does. The bigger, well, let's now think about what's going to happen. This is important to gain some intuition about how this works. What if we were to move these two slits further apart? How would that affect this pattern? Let me ask you this. Is it going to affect the overall shape, or is it going to affect the distance between the fringes?
I think it's going to affect the distance between the fringes.
Or both.
The overall shape between D, which affects theta. I think they're going to get closer together.
Okay, so we have a guess that is, and then so this pattern won't change much at all. And this pattern, as you make the slits wider apart, will get closer together. It's an interesting guess. Anybody else want to take another stab at what's actually going to happen if we take the slits and make them further apart? Could be asking some top hat questions here, but I'm not. Let's just see what happens. We have it. Let's just do it. So take the slit spacing and increase them. Let's watch what happens. Ha, you are correct, sir. Changing, so the widths of the slits aren't changing. We're just moving them further apart. That does not affect the single slit pattern at all. That is determined entirely by how wide these slits are. The fringes are determined entirely by how far apart the slits are. And we know now from our double slit pattern that making them further apart makes the fringes closer together. So we can make this go up and down, slit spacings to change how many of those interference fringes happen in that central maximum. Great. Now, what if we change the slit width? The slit width? So what I was just talking about affects D, not A. That's right. Now I want to move A and leave D the same. What is that going to do to this pattern? If I increase this, I'm going to leave them the same distance apart, but increase the slit size, The overall pattern will get, yikes. Oh, it looks like I'm back. If I did get kicked out, I'm back now. Let me share the screen. Sorry about that. Also, my webcam isn't working today either, so I had to use my laptop. So you're seeing, sorry, part of me that you probably don't want to see. Okay, I think we're back. Okay, let's try it. Slit width, make it bigger. Let's watch what happens. The interference fringe, the diffraction pattern gets narrower, but those interference fringes don't change at all. So one of these, they're sort of independent, right? You can move one, you can move the other, and you should have now some intuition about how that pattern is actually going to change as you change the slit width and as you change the slit spacing. What you probably don't have a decent handle on is what happens if I increase the number of slits. What if I had a third slit or a fourth slit or a fifth slit? Yeah, me neither. Let's just see what happens, shall we? How about a third slit? Interestingly, okay, so they're still spaced out D apart, right? We have a third slit now. Going from 2 to 3 didn't really change where these maxima were, but it did give us much smaller maximum in between each of the individual maxima. So our minima don't happen at the same spot anymore, even though our maxima do. Interestingly, changing this number bigger and bigger and bigger just changes the number of these small little slitlets inside there. If I go all the way to 10, these peaks are not changing at all. They're still in the same location, but they're getting narrower and narrower until you get to something like this. If you've ever shined I think you've done this in Analyt 2 lab, shined a laser through a diffraction grating. Diffraction grating has n equals 100, right? 1,000. What do you see when you put it through a diffraction grating? You're not again, a single wavelength of light, you see each of those orders separated out. And they're not nice wide fringes. They're very narrow fringes because the more of those slits you put together, the narrower those fringes actually get. So you get something that looks like more like that than you do a single or just 2 slits, say. So there you go. All right. We have 5 minutes left in class. I want to give you some advice on the homework. So let me bring it up. Here is my version of Capa 5. So let's just go through them one at a time. Question 1 asks for the width of the slit given a distance between 2 maxima. I've just already told you how to do that. You know what alpha is. Set alpha equal to whatever alpha is with the known value. Solve for A. I think you've got everything else you need to know there. Okay, questions 2 through 7 refer to this plot. Okay, let me make this bigger. So your first question is calculate the slit width, and your second is calculate the slit separation. What is the easiest way to do this? Well, the slit width and separation can be calculated fairly easily if you know where a maximum or a minimum occurs, right? With a single slit, you know m lambda equals a sine theta is a first minimum of the single slit pattern. You've got a single slit pattern here. I haven't drawn the envelope, the diffraction envelope, but if you were, it would look something like this. There is the first minimum. M lambda equals a sine theta right there. At theta equals 5 degrees. That's everything you need to know to figure out what the slit width is. Yeah. What? Oh, well, that's sad. M equals 1 for the m lambda equals a sine theta. Right? This is the first minimum. Now, for m lambda equals d sine theta, you can do the same thing. There's m equals 1, there's m equals 2, there's m equals 3. For the slit width, that's 3. The slit separation, rather, that's d. So the tricky part about this is things are offset a little bit. In fact, I go out as far as you can. There's m equals 1, there's m equals 2, there's m equals 3. Interestingly, m equals 4 is happening right here. There would be a maximum here, but our minimum is destroying it. So 1, 2, 3, this is 4, this is 5, this is 6. You can tell because they should be evenly spaced, right? There's clearly one missing here between here, and that's this one. So 1, 2, 3, 4, 5, 6. If you use the m equals 6, that happens at a nice boom right there. The m equals 6 double slit pattern happens at theta equals 7.5. That should be able, you should be able to solve for D. Okay. Now, 4 and 5 just ask you to plug those values in for A and D to determine what the intensity is at various points. The intensity of the first order interference fringe. They want to know where this is and what its intensity is. So I think 4 asks for the intensity, assuming that the central is 7, and 5 asks you for the second one. So the first one asks you for this one, the second one asks you this one. Those are assuming that A and D are the same and that you're just multiplying the two together. They do not ask you to ask, so, and naively, right? They're going to be slightly different from the place where they should be. These aren't going to be the actual maximums. But assuming those A's and D's, plug them in for where you expect this to happen and just solve for the intensity. The last two questions here are realizing, in fact, what you're going to notice is at 2.5, you expect this intensity peak to actually happen at 2.5. It doesn't. It's a little bit squished in for the same reasons that we've been talking about before. So for 6 and 7, you're going to have to figure out exactly where this guy is. You're going to have to numerically solve for where that thing is. Here is my suggestion for how to do that. You have a function for the intensity as a function of wavelength for the combined double slit interference pattern, single slit interference pattern. We just wrote it down. It's a complicated formula, but you can break it down and make it easy. Put that into a cell in Excel. Give yourself a theta column. Make a whole bunch of different thetas that are pretty close together that go, this is 2.5, this is about 1.25, but I don't know, maybe go from 1.2 to 1.3. And then calculate the actual value of the intensity at each one of those angles. You should be, you can plot it if you want, you can numerically, without even using solver, determine roughly where that thing is. If you want to, you can use solver to maximize the value of that by changing theta. So you can do this in a couple ways. You can do it, you can plot it. You can also have a cell where you've got theta and a plot cell where you've got I, and you can say maximize theta instead of set equal to 0, maximize theta by changing theta, maximize I by changing theta, and it should automatically do what you need it to do to figure out what theta value that is, and also therefore what I value that is. And this then is just going to be they want to know some differences. So they want to know sort of what fraction of it is it off. So take the value you got for 5 and subtract it from the true value and divide it by something to get, and that's the number you're actually going to put in there. But that's all you have to do. You will have to use some sort of numerical technique for 6 and 7, but it shouldn't be too complicated. Okay, I'm out of time. I'll be around on Wednesday morning. If you have questions on homework or exam or anything else, I'll be around Thursday morning in the usual office hours. But I will not see all of you again until Friday afternoon. Have a good week.